Okay, welcome back to another Physical Sciences 3 lecture. We're on page 35, looking at Newton's second law. In the last video, we looked at some examples of Newton's first law in action and just described some of the situations based on Newton's first law. We're going to move on to Newton's second law now, and we've already kind of had a quick look at it in one of the previous videos, but we'll restate it again. An object's acceleration is directly proportional to the net force on it and inversely proportional to its mass. This law is usually expressed in the following formula here. So this formula here, F net, so the net forces equal ma, which is equal to, this is the Greek letter epsilon, and it means the sum of all, and then we've got the F in there, forces, sum of all forces. Okay. Sum of all forces acting on the object. So when you have all the forces acting on the object, then you can calculate them all up, add them all together with the directions included, and then the net force, so the overall force, is going to be what the result is of those additions. Okay, so we've got F net is the SI unit for that is newtons, so it's named for Isaac Newton. M is the mass of an object in kilograms, and A is the acceleration of the object in meters per second squared. So they're all in SI units. Note that net force and acceleration are vectors, and the acceleration must be in the same direction as the net force. So whichever direction that net force or the overall forces add up to, then that's the direction of the acceleration. If the net force is 0, the object is not accelerating. But it doesn't mean that forces aren't acting on it. You might have a body like our balls, and all of them are balanced. So this like F net equals 0, but it just means that all the forces are balanced. They might all be the same, or they might be the same directions or whatever. So as long as they're equal in the directions that we're looking at, then the force is balanced. It could still be moving, just not accelerating. Alright, and finally, the weight formula, F equals mg, is an example of Newton's second law. So again, this is Fg is equal to mass times acceleration. G is acceleration due to gravity. Okay, acceleration due to gravity, good. Let's have a look at some examples. An 800 kilogram car accelerates from rest. Remember, that's our initial velocity, u equals 0, from rest to 20 meters per second. So that's going to be our v in time 6 seconds. What is the average force being exerted on the car during this period? Alright, so F net equals ma. So in order to work out what force, we need to work out the acceleration. And luckily for us, we have v equals u plus at from our equations of motion. And we can rearrange this, so we have a is equal to v minus u over t. And then a is going to be equal to 20 minus 0 over 6. And that is equal to 20 divided by 6. 3.3333. Good. So I'm just going to do 3 significant figures, and that is in meters per second squared. Okay. And now we just need to put that into our equation here. So we have how heavy is it? 800 kilograms times 3.33. Let's go to our calculator times. And we're going to do it to 3 significant figures. So we're going to say it's 2,670 newtons. Okay, and these are the 3 significant figures. Great. Okay, in this example here, question 6, we have the brakes of a 3-ton truck exert a stopping force of 4.5 kilonewtons. If the truck is initially travelling at 72 kilometers per hour, what will its acceleration be, and how far will it travel? Let's just draw a little diagram of our truck. Okay, so we have a 3 ton, so it's a 3 ton, so that's 3,000 kilograms. That's what 3 tons means. 3,000 kilograms. Okay. Truck exerting a force of 4.5 kilonewtons, so remember that's 4,500 newtons. So we want these in SI units, and it's initially travelling at 72 kilometres an hour. So I'm going to write down through that. So I like writing down through that. It helps me think about what I've actually got. So 72, and we have to divide that by 3.6 to get that into metres per second. So remember our kilometres an hour to metres per second conversions. So 72 divided by 3.6 is equal to 20. 20 metres per second. Very good. It comes to rest, so that means our final velocity this time is equal to 0. Acceleration, we don't actually know what our acceleration is, because we've got our frictional forces acting this way. The brakes of a 3-ton truck exert a stopping force of 4.5 kilonewtons, so that's our 4,500 newtons going that way. Truck is initially travelling at 72. What will acceleration be, and how far will it travel? So we have obviously the force of gravity, and so if we wanted to include all of them, we have force of gravity, and we also have the normal force, and they're equal to each other. So, but the only force we really need to worry about is this frictional force here. That's that way. And if the frictional force is acting in that direction, then we know that acceleration is also acting in that direction as well. Okay. So we have to label which direction is positive as well. Remember, we always have to do that. So we're going to say that the direction of motion is positive. So direction of initial motion or of motion is positive. So we have to define that. Positive. I felt like I spelled that wrong somewhere, but I think that's okay. Direction of motion is positive. So that means that this 4,500 newtons is negative. Okie doke. Alright, so what will its acceleration be, and how far will it travel before coming to rest? So before we find out its displacement, we need to find its acceleration. Do we have a time? We don't have time. That's okay. So we can find out its acceleration. So F net equals ma. Okay. And so, like I said before, these forces will just cancel out. So the only force we have to worry about is this one. So that's going to be our negative 4,500 is equal to a 3 ton, so 3,000 kilogram truck times by A. So then negative 4,500 divided by 3,000 is equal to A, so that means that A is equal to negative 1.5 metres per second squared. So that makes sense. So the acceleration is against the direction of motion, so A is equal to negative 1.5. And then we need a direction, don't we? Negative 1.5 metres per second. Positive. So opposing. So A is equal, that's opposing motion. Okay, so the braking force is a type of frictional force. Opposing motion. So that's our acceleration taken care of. Now we want to find out our S. And I'm going to use, which one? I think we'll use V squared equals U squared plus 2AS. Okay, because that means that V squared is going to become 0 equals 20 squared plus 2 times negative 1.5 times by S. Okay, so let's subtract, well, 20 squared is equal to 400. So we're going to have negative 400 here. 2 times negative 1.5 is negative 3, divided by negative 3 is equal to S. So therefore, S is equal to 400 divided by 3 which is 133 metres to 3 significant figures in original motion. In original motion. In direction of original motion. Okay? So 133 metres in the original direction. Okay, we'll leave that one there. We'll put the next example in the next video.